In the vast tapestry of scientific history, few figures have left as indelible a mark as Stephen Hawking. His brilliant mind not only illuminated the darkest corners of our universe, but also demonstrated how even the most profound mistakes could lead to revolutionary discoveries. In a field where precision and accuracy reigned supreme, it was paradoxically a significant error that would help reshape our understanding of one of the universe's most mysterious phenomena: black holes. Born in Oxford, England on January 8, 1942, coincidentally 300 years after Galileo's death, Hawking showed early signs of exceptional intelligence, though not always in conventional ways. His school friends nicknamed him Einstein, recognizing his innate curiosity and unique way of approaching problems. Despite his father's wishes for him to pursue medicine, Hawking's fascination with the cosmos led him to study physics at University College, Oxford, where his natural brilliance allowed him to excel with minimal effort. However, fate had different plans for the young physicist. During his graduate studies at Cambridge University, at the age of 21, Hawking received devastating news that would alter the course of his life. He was diagnosed with amyotrophic lateral sclerosis, ALS, a progressive neurodegenerative disease. Doctors gave him just 2 years to live. This dark prognosis could have ended his scientific career before it truly began, but instead, it sparked an extraordinary determination. As his physical capabilities declined, his intellectual prowess seemed to grow stronger, leading him to focus intensely on theoretical physics, a field where the mind, not the body, was the primary tool. It was during this period that Hawking began to grapple with one of the most perplexing phenomena in the universe: black holes. These cosmic behemoths, formed from the collapsed cores of massive stars, were thought to be so gravitationally powerful that nothing, not even light, could escape their grasp once it passed their event horizon. The prevailing theories of the early 1970s painted black holes as cosmic prisons, absolute in their finality, perfect in their imprisonment of matter and energy. The scientific community had largely accepted this view, building upon Einstein's general theory of relativity, which suggested that information that fell into a black hole was forever lost to the universe. This concept aligned perfectly with the classical physics understanding of black holes as cosmic dead ends, where the laws of physics as we knew them ceased to function. However, in 1974, Hawking made what he initially believed was a critical error in his calculations regarding black holes. Working late one night, frustrated and emotional about a recent argument with a colleague, he hastily concluded that black holes must emit radiation, a finding that seemed to contradict everything physicists thought they knew about these cosmic objects. When he first announced this possibility to his peers, the reaction was one of skepticism and disbelief. After all, how could something from which nothing could escape possibly emit radiation? The scientific community's initial response was predictably harsh. Many of his colleagues viewed this proposition as not just incorrect, but as potentially damaging to the field's understanding of black holes. Some saw it as a moment of weakness from a brilliant mind perhaps affected by his personal struggles. Others dismissed it as a mathematical error that would soon be corrected. What nobody realized at the time, including Hawking himself, was that this apparent blunder would lead to one of the most significant breakthroughs in our understanding of black holes. The mistake forced Hawking to rigorously examine his calculations, leading him down a path that would eventually reveal a fundamental truth about the nature of these cosmic phenomena. His initial error, born from a moment of emotional haste, had inadvertently opened the door to a new realm of theoretical physics. The irony of this situation wasn't lost on Hawking. Here was a man who had built his career on precision and mathematical rigor, yet one of his most important contributions to physics initially stemmed from what he thought was a mistake. It served as a powerful reminder that in science, as in life, our greatest breakthroughs often come from questioning our most basic assumptions, even when those questions arise from apparent errors. Looking back at this pivotal moment in theoretical physics, we can see how Hawking's willingness to challenge established theories, even through what he initially perceived as a mistake, exemplified the true spirit of scientific inquiry. His apparent error forced the scientific community to grapple with new possibilities and ultimately led to a deeper understanding of one of the universe's most enigmatic phenomena. This period in Hawking's career perfectly illustrates how scientific progress often occurs not through linear advancement, but through a series of challenges, mistakes, and reconsiderations. The blunder that initially seemed to threaten his scientific reputation would eventually become one of his most celebrated contributions to our understanding of the cosmos. In the 1970s, Hawking initially held a widely accepted belief. Black holes were perfectly insulated regions of space where nothing, not even light, could escape their gravitational grip. It was a concept that fit comfortably within Einstein's framework of general relativity. However, Hawking's early calculations about black holes contained a flaw, one that he soon recognized as an opportunity rather than a defeat. Realizing the limits of his initial approach, Hawking revisited the equations governing black holes. This time, he ventured into the uncharted territory where quantum mechanics and general relativity intersected. By combining these two fields, Hawking began to uncover a surprising possibility. Black holes were not the absolute cosmic prisons everyone thought they were. This bold reevaluation led him to propose something revolutionary. Black holes, he theorized, were not entirely black. Instead, they emitted tiny amounts of thermal radiation, a phenomenon now famously known as Hawking radiation. Hawking's insight into black holes came from an unlikely interplay of ideas. Using quantum mechanics, he theorized that pairs of particles constantly pop in and out of existence in empty space. Near a black hole's event horizon, the invisible boundary beyond which nothing can escape, one of these particles could fall into the black hole while the other escapes into space. The escaping particle would appear as radiation, while the black hole gradually lost mass in the process. This finding turned the prevailing understanding of black holes upside down. Instead of being eternal, black holes could eventually evaporate over vast stretches of time, shrinking as they radiated energy. Hawking's calculations revealed that black holes were not as permanent or invincible as Einstein's theories suggested. The implications of this discovery were staggering. Not only did it challenge the notion of black holes as cosmic endpoints, but it also raised deeper questions about the fundamental workings of the universe. Could black holes destroy information, define the laws of quantum mechanics? Or could they hold the secrets to unifying quantum theory and general relativity? Though initially met with skepticism, Hawking radiation became one of the most celebrated theories in astrophysics. Scientists marveled at Hawking's ability to blend quantum mechanics and general relativity into a single narrative, one that hinted at a grand, unified theory of everything. Before Hawking's groundbreaking work, black holes were regarded as enigmatic but relatively straightforward objects defined by their mass, spin, and charge. Hawking's revelations forced scientists to rethink black holes as dynamic systems capable of change and interaction with their surroundings. The idea that black holes could emit radiation and eventually vanish also unsettled the scientific community's understanding of thermodynamics. Hawking demonstrated that black holes obey the same laws of entropy and energy conservation as other physical systems, linking these cosmic giants to the microscopic world of particles. This fusion of the macroscopic and microscopic was unprecedented. Hawking radiation became a powerful symbol of how two seemingly incompatible domains of physics, quantum mechanics and relativity, might coexist. It offered a tantalizing glimpse of a deeper, underlying reality that science had yet to fully comprehend. Hawking's discovery of Hawking radiation propelled him into the spotlight, earning him accolades and a place among the most influential scientists of the 20th century. He became an icon of intellectual resilience, celebrated for his ability to see beyond conventional thinking and embrace complexity. Hawking radiation not only transformed black hole science, but also became a cornerstone of modern cosmology. It opened doors to exploring the mysteries of the universe at its most extreme scales, from the behavior of matter at quantum levels to the origins of the cosmos itself. For Hawking, the discovery was not just a scientific achievement, but also a testament to the power of intellectual curiosity. Despite his physical limitations due to ALS, Hawking's mind transcended boundaries. His work showed that even in the face of adversity, profound insights can emerge. Hawking's insights into black holes reshaped our understanding of the universe, laying the groundwork for future research in fields like quantum gravity and string theory. His work inspired countless scientists to explore the interplay between the largest and smallest scales of existence. Moreover, the discoveries sparked philosophical debates about the nature of reality. If black holes could evaporate, what happened to the information they swallowed? This question, known as the black hole information paradox, continues to challenge physicists today, demonstrating the enduring influence of Hawking's ideas. What makes Hawking's journey so extraordinary is not just the magnitude of his discoveries, but his ability to transform a perceived mistake into a monumental breakthrough. His willingness to question his assumptions and embrace new possibilities exemplifies the essence of scientific inquiry. Hawking once said, "Intelligence is the ability to adapt to change." His life and work embody this principle, proving that adaptability and open-mindedness can lead to revolutionary insights. Stephen Hawking's journey from error to enlightenment is a testament to the power of perseverance and intellectual courage. His discovery of Hawking radiation not only advanced our understanding of black holes, but also demonstrated the profound connections between quantum mechanics and general relativity. Hawking's story reminds us that mistakes are not the end, but the beginning of deeper understanding. His legacy challenges us to remain curious, question assumptions, and embrace the unknown. If you're inspired by the incredible story of Stephen Hawking and want to explore more groundbreaking ideas in science and technology, subscribe to Tech Titans. Join us as we unravel the mysteries of the universe and celebrate the minds that shape our understanding of reality. Don't miss out. Hit that subscribe button now.